A user pastes a standard snippet of text into a comment box on a web application. Instantly, their active session is hijacked, and the underlying database is compromised. The text they pasted was executable code. The engineering question is how the browser was tricked into running it. Web security at this level rarely involves breaching external firewalls. It relies entirely on understanding and manipulating the browser's implicit trust model. We can map this trust model into 4 defensive zones: DOM parsing, header policies, cookie storage, and network protocols. When a page loads, data moves sequentially, hitting the network quadrant, validated by header policies, retrieving credentials from cookie storage, and finally interpreted by DOM parsing. These 4 handoffs define the perimeter of browser security. Mastering them allows us to build systems that maintain integrity even when handling untrusted data. This stylized scanner demonstrates how a browser parses an HTML string. Notice what happens when it hits a script tag. It switches abruptly from a blue text rendering mode to a red JavaScript execution mode. The parser makes no distinction between code you wrote and code injected by an attacker. It reads the string as an instruction block and passes it directly to the execution engine. This is cross-site scripting, or XSS. Think of a retail suggestion box. Customers drop in feedback notes. If someone drops in a note that says, "Read this out loud and embarrass yourself," and the staff blindly follows the instruction without realizing it's a trick, the system fails. In a standard Express or React application, this failure happens when developers use raw string concatenation to render user input directly into the HTML output. Specifically, assigning raw data to properties like inner HTML or React's dangerously set inner HTML bypasses the native protections built into modern frameworks. Trying to filter out bad code using regular expressions usually fails because attackers easily obfuscate their payloads. The secure approach is output encoding. You must explicitly sanitize the data. Modern frameworks handle this automatically if you use safe properties like text content, or you can use dedicated libraries like DOM Purify for more complex needs. Here's the fix in action. We place a DOM Purify filter block in the rendering pipeline. When malicious brackets enter, they are encoded into their character entity equivalents. The scanner now reads these as literal symbols instead of executable markers. Trusting unescaped user input in HTML output is the architectural flaw that makes cross-site scripting possible. Output escaping works, but large codebases rely on thousands of developers. A structural failsafe is required for when a single line of code is inevitably left unescaped. That failsafe is the content security policy. Notice the injected script attempting to execute and reach outward, only to have a massive structural wall slam down to block the connection. CSP acts like a bouncer with a VIP list. The wall checks the domain. Because the request to evil.com is not on the whitelist, the browser rejects the connection before the script can ever load. CSP is delivered as an HTTP response header. A strict policy might start with the directive default source self, which instructs the browser to load assets exclusively from the site's own domain. If you use a third-party CDN or an external analytics platform, you explicitly add their specific domains to this whitelist. By default, a strong CSP also completely disables inline script execution. If an attacker injects a script tag directly into the DOM, the browser simply refuses to run it. A content security policy limits the blast radius of a successful XSS injection, making it a mandatory piece of your defensive architecture. Fixing XSS introduces a new architectural trade-off. Look at this balancing scale. Using local storage for authentication tokens leaves you exposed to XSS extraction, but swapping to an HTTP-only cookie shifts the risk entirely to cross-site request forgery. Local storage is completely accessible via JavaScript. If an XSS attack succeeds, the attacker can write a single line of code to read your tokens and send them to their server. You can solve this by storing tokens in an HTTP-only cookie. This flag tells the browser to block all JavaScript access to the cookie, closing the XSS extraction vector. However, relying on cookies opens the door to CSRF. This attack is equivalent to an attacker forging your signature on a blank check that your bank then processes as legitimate. Here is the attack path. You log into your bank. In another tab, you click a malicious link. That malicious site contains a hidden form that automatically submits a post request to your bank server. Watch the network behavior here. As the malicious tab fires its payload to the bank, the browser automatically attaches the bank's active session cookie to that data stream. We can restrict this behavior using the same site attribute. With same site equals lax applied, a padlock secures the cookie. When the cross-origin payload attempts to grab it, the padlock holds firm. Same site provides strong baseline protection, but certain complex navigation flows can bypass it. For state-changing operations, you need an explicit verification step. This is the anti-CSRF token. The server generates a unique cryptographic string and sends it to the client. The client must include this exact string in the header of any request, so the server can verify its origin. Securing authentication state requires choosing a mitigation strategy. Cookies require strict CSRF protection, while local storage demands absolute XSS elimination. Security extends beyond the client's local memory to the network layer, where strict rules govern how different domains interact. Here we have two isolated server islands, a front-end domain and an API domain. They are separated by a chasm, and a tollbooth labeled Browser SOP completely blocks the bridge between them. The same origin policy dictates that a web browser permits scripts on a first page to access data on a second page only if both pages share the exact same protocol, host, and port. Cross-origin resource sharing, or CORS, is the specific visa process used to safely bypass the SOP tollbooth. A critical detail often misunderstood is that CORS is enforced entirely by the client's browser, not the destination server. When your front-end code uses the Fetch API to request data from a different domain, it triggers this mechanism. Watch the tollbooth send an options scout across the bridge. This is the pre-flight request, asking the API island if the front-end domain is authorized to communicate. The API island stamps the scout and returns an Access Control Allow Origin ticket. The browser reads it, the barrier lifts, and the actual request data flows across. Developers frustrated by CORS errors often configure their servers to return a wildcard origin. Doing this while allowing credentials breaks the isolation model entirely, exposing the API to any malicious site. CORS is not a firewall designed to keep hackers out. It is a set of headers that tells the browser it is safe to relax its own same origin policy for trusted clients. Pulling back, we see the entire defensive matrix. The four quadrants interlock. DOM parsing handles XSS, header policies enforce CSP, cookie storage manages CSRF, and network protocols govern SOP and CORS. Watch a safe user action flow through this environment. The packet moves sequentially, repelling attack vectors at the network, state, header, and DOM boundaries. In production, these layers are heavily dependent on each other. Securing a cookie means nothing if an XSS payload can rewrite the DOM, and a strict CSP is useless if a wildcard CORS policy exposes the API. By mastering the precise mechanics of these four boundaries, you ensure your front-end architecture remains resilient and secure in the real world.